So by now, you should be used to everything in eukaryotes being more complex than prokaryotes, and the same thing holds true for transcription. The first idea is there are multiple polymerases, and we're talking RNA polymerases. RNA polymerase 1 transcribes rRNA genes, all rRNA genes except for the 5S rRNA. RNA polymerase 2 transcribes all mRNAs. So this is the one that most everything we're talking about is centered around, because these are the protein coding genes. It also transcribes most snRNAs, LNC, so small nuclear, long non-coding, micros, and small nucleolar RNAs. And we will talk about these in a couple chapters from now. And then RNA polymerase 3 does the tRNAs and the 5S rRNAs, and then some that's not met by RNA polymerase 2. So RNA polymerase 2, mRNAs, okay? 3T, if that will help you. So RNA polymerase 3 transcribes tRNAs. Most of these resemble the same complex, and they are very similar to what you find in bacteria as well. So clamps, lids, rotors to help this come through. They have this sort of looks like a hand, so like the palm of the hand with the fingers and the thumb. And it's just feeding the DNA through and sending the RNA molecule out. This is how they're getting in the loose nucleotides. Now for regulatory sequences, here we have our core promoter. In eukaryotes, it's common to find a TATA box, and then there's also a consensus sequence around the transcription start site. The TATA box is usually -25. What does that mean? 25 base pairs upstream of the start site. Start site is +1. This should be familiar from when we talked about bacteria. If all you have is this core promoter and then your sequence of interest, you'll have basal levels. So these are low levels of transcription. You're making the bare minimum. However, to increase that, we have these regulatory elements. So this is where we can bind our silencers, our activators, and things like that that will control the rate. Once we have this going on, we can ramp up how many transcripts can come out over time, okay? So this like to say if the basal levels are 5 transcripts an hour, if we have an activator, we might get 200 transcripts an hour, okay? So basal levels, low levels, this thing is working, but it's working at its bare minimum. You add a regulatory element, you can either stop it or ramp it up significantly. I'll also note here that the regulatory elements and the promoters, these things that help to get transcription started, are cis-acting. Cis meaning next to. So they are usually on the same chromosome near the gene that they're coding for. But the factors that bind to it, so polymerase and activators and silencers, are transactin factors across. So these are transcribed by different genes that usually exist far away from the gene that they're going to act on, okay? So cis-actin elements or sequences, transactin factors that bind to those sequences. Some of those factors are, so RNA polymerase 2 here, because most of what we're talking about is going to be PAL2, general transcription factors. So we're going to go into a little bit of detail about just these 5. So TF2D is T for transforming, F for factor, 2 for polymerase 2, and this is just type D. So these are transcription factors for polymerase 2 and whatever the type is. D has this TATA binding protein and allows it to bind to the TATA box. H has a helicase activity and helps switch from initiation to elongation. And mediator has also been described as a factor that helps us with that switch from initiation to elongation in eukaryotes. If you want more detail about what they do, this is provided for you for your convenience. But you'll see here, RNA polymerase 2, 12 subunits, some of them similar to the beta found in bacteria. 2D has this TATA binding protein. B binds to D and helps RNA polymerase II to bind. So you'll see these things are binding and attracting other things to bind. So the same here, S binds polymerase, helps polymerase bind to the promoter in B, and then tells E and H to bind to the polymerase. Again, most of what we're talking about is describing RNA polymerase II and its promoter and its initiation and its elongation and its termination. 1 and 3 have different promoters than these that we're going to talk about, and they're usually an internal promoter. So here we have the gene, and inside of the gene, not before it, like we find with polymerase II, but inside the gene is where its promoter lies, where it's to bind and to start transcription. So for polymerase II, in eukaryotes, TF2D with its tau-tau binding protein binds to the tau-tau box that is upstream of the transcription start site. TF2D tells TF2B, hey, come bind in this area with me, we're trying to transcribe. TF2S binds to RNA polymerase II and together bind to the core promoter because TF2B is saying, hey, bind to me. So TF2B binds to the tau-tau binding box. It attracts TF2B. TF2F binds to the promoter, binds to the polymerase, and then with the help of TF2B, binds to the promoter. TF2F also says, hey, to E and H to come bind to the polymerase. And now we have our pre-initiation factor. This is closed, okay? We haven't opened up our DNA yet. So remember, H acts as the helicase that's able to open the DNA and give us the open complex. So H comes along and phosphorylates the carboxyl terminal domain of RNA polymerase II. When it does that, it breaks the contact, so it's kicking off B, E, and H. And so F stays bound to polymerase as it was before and opens up and is able to now transcribe. This is initiation, and mediator comes in some way that allows us to go to elongation. If we look at this in a different way, so our regulatory promoter, our core promoter, remember core promoter, basal level. We have our tau-tau binding box, TF2D with its TBP binds to the tau-tau box, attracts all of these things that come along. Now they're binding and we're able to kick some things off and go. Here we have an enhancer. So remember, enhancer will bind to the regulatory promoter. And you can see this looping around to allow it to interact with our polymerase here. You'll also see just a bunch of factors in this looping to show you that it's not necessarily a neat process, but things have to get in close proximity. And if these regulatory factors are located at a distance, that they loop the DNA in so that they can interact with the gene that it's meant to interact with. Okay? And we're okay with this. There is no primers here. RNA polymerase II is capable of doing everything that needs to be done. The DNA opens up in just the area that's being transcribed and closes behind it, and the area in front of it is also closed, so it just goes along opening and closing as needed. So for elongation, we would just keep chugging along this DNA, building our RNA transcript, closing that DNA behind us, until we get to termination. Also similar to prokaryotes, there are two ways to do this. So the allosteric model or the torpedo model. Here you should notice that the allosteric model resembles row independent and the torpedo resembles row dependent. So RNA polymerase II comes along, transcribes everything past this polyadenylation sequence. Polyadenylation means a bunch of adenines. So think about the poly A tail. This is the sequence that codes for it. So after we have transcribed this, the RNA is cleaved. Okay, so we're going to come along in here and cut that RNA. This RNA is free to go on, but this polymerase hasn't got the message yet that it should stop. So it's still going on making the RNA transcript. Now two things can happen. One is it destabilizes and dissociates because the elongation factors are released and termination factors bind. It causes it to be kicked off. Two is this torpedo model that after it kicks off the mRNA, an exonuclease binds to it and starts eating that RNA as it's chasing after polymerase. And once it catches up to polymerase, it can kick it off. Okay, so that should remind you of what role it's doing. Again, like the Pac-Man model. So here are our two models. One is the allosteric, that it disassociates. This will probably also be due to like the binding of polymerase to the DNA is unstable after a while because of what it's actually transcribing. The other is something goes along, catches up with it, and kicks it off. These are our two possible mechanisms, okay? We're still doing research to figure out which one it is, but so far it looks like, maybe it's a combination of two. So this is transcription in eukaryotes. We have 3 polymerases, we have our basal apparatus, and then we have our regulatory. We have 2 ways to terminate, okay? 5 transcription factors to become familiar with. Remember that what we're going to talk about, we spend most of our time on RNA polymerase 2 mechanisms, but 1 and 3 are here, and they do different things, okay? So it's not a one-size-fits-all.